Work actually transfers energy, and energy is the capacity to do work. For example, look at here, work done on the briefcase by the person carrying it up the stair in the figure stores energy in the briefcase earth system. So our system is briefcase and earth system. So for example, um, in this case, say for example, the person lifts the suitcase at the top here, then it stores as this work is stores as gravitational potential energy, gravitational potential energy. Okay, so there are various forms of energy such as kinetic energy, potential energy, heat energy, chemical energy, electrical energy, and the nuclear energy. This kinetic energy and potential energy is also called combinedly or separately as mechanical energy. Mechanical energy. So mechanical energy is the sum of kinetic energy and plus potential energy. Let's talk about these two energies. Kinetic energy is the energy an object has due to its motion. Say, for example, say this is in the ground, a ball is rolling. Say, ball has the mass m, and it is rolling with a speed v, for example. Then in that scenario, the kinetic energy, kinetic energy equals kinetic energy equals half m p squared. Okay, so the unit of kinetic energy equals kilogram meter square second square, and this is equivalent to joule. All the unit of energy is joule. Okay, this is about this energy, kinetic energy. Let's talk about the potential energy. Potential energy is the energy stored in an object due to its position, structure, or the configuration. So in this example, work done against the force due to earth, this is the gravity, in lifting an object becomes potential energy of the earth object system. So for example, let's look at here. If you want to lift um, this object from this ground level to this point at a height h, so this height is h, so we want to lift this bag maybe from this level, ground level, we call it the reference level, for example, because we start to lift from this point, so this is the reference level, and this height is h, so we call it final position. This is initial position, reference level. This is the final position. So the height is h. So in this case, we define change in potential energy, delta PE. So this represents change in gravitational potential energy, which equals m g and h. So here m is the mass of the object. For example, in this case, this bag or this object is lifting up. G is acceleration due to gravity, due to gravity, and h here is the increase in height. Increase in height. Okay. So, for example, in here in this level, reference level, if we talk about that reference level, um, for reference level, say potential energy is, say, for example, 0, then at height h, potential energy due to Earth, potential G equals to mgh. So we can say that change in gravitational potential energy equals mgh. Okay, so clearly this gravitational potential energy is basically work done by external force against gravity, and this work is stored as gravitational potential energy. Let's go to the elastic potential energy. This is the energy stored in a string, energy stored in a string when it is compressed or it is elongated. Okay, in the given figure, look at here, this is the uncompressed spring, uncompressed, or we can say not elongated, not stressed spring. When the external force is applied, when we apply the external force to pull, that this is the change in length. That represents the change in length. Change in length. Say, for example, if this length, say this length is L, or say X naught, then this length is, after applying the external force, say this length is X, then in this case, the change or the increase in length, change in length will be X minus X naught. Okay. Instead of X, we say X1. So this change will represent by X. So basically, sometimes we can equivalently you can write change in X. So these are just the symbols. Okay. So when the spring gets elongated or compressed, it stores potential energy. We call it elastic potential energy, which equals half kx squared. So here, this k is called spring constant, right? So each spring will have different spring constant, and clearly this elastic potential energy is basically work done by external force, in this case, I mean applied force, because we are pulling this spring from this point. So the change in length is this, applied force when the spring is stressed by length x, In this case, this x represents the change in length. So clearly this is energy. So unit of elastic potential energy will be certainly joule. Okay. Let's go to the Hooke's law. In Hooke's law, it basically uh, gives the relation between the the applied force and how much change happens in the length of a string. Just see the one example here. Say this is the actual length, uncompressed length. This is the spring. This side is fixed. If we apply the external force, then it will be here. Say, for example, we apply the external force F. So here F is the external force. So clearly, as before, this represents the change in length. This is X. Okay. This represents the change in length. Let's suppose what will happen if the external force is removed. If the external force is removed, the spring returns to its original shape. Means it comes to this. This is the original shape, original length. Okay, because of force exerted by the spring. This force exerted by the spring is also called restoring force. Right? Restoring force. So the positive value of this magnitude of restoring force is same as external force. We call it deforming force. That is basically the applied force, applied external force. Okay, so we can write Hooke's law as this is the Hooke's law. We can write F equals minus kx. Okay, so here F represents the restoring force, that, and this x represents the change in length. In this case, change in length, and k is clearly the spring constant. So clearly this minus sign, this minus represents that F, which is the restoring force, and x is the displacement, are in opposite. Okay. Based on this concept, you can practice this example, practice problem 1. Similarly, practice problem 2. This is practice problem 3. This is practice problem 4. And finally, practice problem 5.